Thank you very much. First of all, the organization of this conference, for different reasons. First of all, for a wonderful job of the organizers, and especially Mohammed. Thank you very much for everything. Thank you very much for meeting such a nice group of people, colleagues, and not only that, also young people around, which makes the conference even more exciting to see future generations working on differential geometry. As you see, the blackboard or whiteboard is going to be the center of my work now. So the screen is going to be check TX input signal for 1 hour, I'm sorry. And I hope it's going to be okay. And actually for the microphone, I don't know actually, is this a microphone or? Okay. But I think that I speak loud enough for a good understanding of what I'm saying, right? So as Professor Calvaruso said, I'm going to talk about Ambrose-Singer theorem for symplectic manifolds. Okay, to put the things into the ground, let's talk first about Ambrose-Singer theorem. So, by the way, I'm sorry, just a second, because I have some notes, and in particular the years of some papers that I don't remember by heart. So Ambrose-Singer theorem, I mean Ambrose-Singer have two famous theorems, but this one is concerned about homogeneous spaces, and the theorem says, it comes from the 50s, that if M is connected, simply connected, and complete manifold, Riemannian manifold, then the manifold is homogeneous if and only if there exists a connection, linear connection, satisfying these conditions. The connection is a metric connection. It has parallel curvature and parallel torsion, right? Or actually, instead of that, you can put this, where this is the difference between the connection and the Levi-Civita connection. So this is the old result, which produced important, I put the eraser somewhere, and it's here, but I don't know where. Okay, thank you so much. Important results, by the way, some of the statements focus on the existence of this connection, or sometimes it focuses on the existence of the difference. It's the same. Either you define through the connection, or either you define it by the existence of this is a tensor. The difference of two linear connections is a tensor, right? So this result is a powerful result for different reasons. And the main reason is because you can make algebra, and you can mix algebraic tools in the following way. If you have one of these manifolds and you pick a point, and you consider the tangent space at that point, then the condition being metric is the same at that point that the difference satisfies this condition. So the possible tensors which could be included in the Ambrose-Singer theorem at each point are or belong to this space at each point, and we can decompose this space by the action of the orthogonal group, and this space splits, actually this S, now we can understand it as a Biography notation as a 3-tensor with the musical operator. So it splits into 3 classes, irreducible classes by the action of the orthogonal group, right? And then it happens that if Sx belongs to one of these classes, then this Sy belong to the same class for the other points of the manifold. Right? So you use this fact and you classify this tensor at that point and you get information and you get nice results. This is classical stuff. For example, nice results could be of the following type. Could be, for example, if the tensor belongs to the first class, then the manifold is homogeneous and it has constant curvature. Or if it belongs to T3, then is naturally reductive. And there are more results, right? So the idea is that this tensor provides information through algebraic tools. Okay, so this is the beginning of the story. The result was generalized in many different situations. Actually, the core of my talk is going to be another generalization of that. But I think that this final generalization is, in some sense, perhaps one of the last possible generalization of the result. In any case, I mean, we go some years later. Oops, it's going to take, it's like working out. Good. And that's the reason I need the papers. I need some historical recall of the results. In 1992, if you drop the topological conditions, I mean, you drop completeness, you drop simply connectness, and then what you have is a characterization of locally homogeneous spaces. So the existence of this connection satisfying the conditions of the Ambrose-Singer theorem. This is a result of Tricheri. And then you go, for example, to 1997. And then you have the result for pseudo Riemannian manifolds. In this case, you have a characterization of those pseudo-Riemannian manifolds that are homogeneous but reductive homogeneous, because in the realm of pseudo-Riemannian manifolds, being homogeneous is not equivalent to being reductive homogeneous, even though in the Riemannian setting, yes, any homogeneous space is reductive homogeneous. You know that reductive is not the first time in these days. Actually, we found that word. So that means that the Lie algebra splits into different subspaces, and the action of the adjoint action of one of the spaces leaves invariant the other space, right? So we have this, right? Okay. And then this is 97. Yes? I tried this one. Thank you, Giovanni. Okay, I don't know if it's much better, but I think it's basically the same. No, it's fine, because I do my working out. Then you go to, let me see the year, in 1980, and then also to have a complete proof in 2014, to have a similar result in the case you have a pseudo-Riemannian manifold, and there is a set of tensors defining some kind of geometric structure. For example, it can be a Riemannian manifold, or pseudo-Riemannian manifold, and an almost symplectic structure, for example, or a quaternion Keller structure, a structure defined by tensor or a set of tensors associated with a connection, with a metric. So in that case, we have reductive homogeneity. If and only if, and with homogeneity I mean that the action of the isometry group is transitive, and at the same time it leaves invariant the geometric structure. For example, if the manifold is almost complex, the group of isometries are almost complex holomorphic transformations with respect to the almost complex structure. So if there is this structure, this homogeneity, if and only if there is one of these connections, complete connections, such that the same. The curvature vanishes, the torsion vanishes, the metric is parallel with respect to the connection, and the tensors are also parallel. Okay, so this is the story. So one can reflect a little bit on this situation and think of possible generalizations in different directions. And the work we have done is working with the idea of dropping this connection, this metric. So instead of having a geometric structure on a Riemannian manifold, which could be a reduction of the orthogonal frame bundle, for example, like in Berger list we had yesterday, instead of that, we can think of a geometric structure that doesn't depend on a metric structure before, as for example, symplectic manifolds. So symplectic manifolds are defined by a tensor, but you don't really need a metric tensor behind to define the symplectic structure. Actually, on the contrary, many of the times you really need to work with a manifold with a symplectic tensor and without any possible metric behind. We'll go back to that situation afterwards. So there are different attempts of trying to study homogeneity in non-metric spaces, and our work, because when I say our, it's because the result I'm going to show, it was a collaborated work with José Luis here. Thank you very much, Professor Carmona. So it was a couple of years ago. So that means in 2022, and we have the following. So the statement is actually very similar to the one of the classical result. So we have a manifold with a tensor or a set of tensors. So it can be 2 or 3 tensors. Let me put them just T. Oh, thank you. I don't know if this one is better. Yeah, I think so. Thank you, Mohammed. So this is a manifold, so that, okay, we can put complete, connected, simply connected. So reductive homogeneous is the same as the existence of a complete connection such that the conditions that now they are familiar to all of us are satisfied. Right, so no metric connection here, nothing, there is no Levi-Civita connection, there is just a manifold with a tensor, and the result is the standard one, the expected one, right? In particular, if P is a metric, you put here the derivative of the metric, and you have classical Ambrose-Singer theorem. But now you can put any geometric structure defined by a tensor here. So we have this result. Okay, once we have the result in our hands, we wanted to put it somewhere where we're going to study something new. And that's what we did with symplectic geometry. So we took a symplectic manifold and we studied homogeneity on symplectic manifolds, which is a very classical topic in many books, many papers on topological and geometric symplectic and the symplectic realm. And we tried to explore the applications of the result in the philosophy of trying to find these classes as the 3 classes we had before in the case of the symplectic geometry. And we have these results, and this is going to be the rest of the talk, actually. Okay. I'm going to use probably the blue one. And the blue one is going to be easier, probably. Okay, so if we want to continue the same philosophy, what we have to do, I said in advance and now I write it, you fix a point and you have to define some classification of tensors at that point, with the hope that that classification will span or will be transferred to any other point of the symplectic manifold. And that's the case. I'm going to try the blue one. So now we have a symplectic manifold, right? So imagine you have one of these tensors, one of these connections satisfying the conditions of the theorem, and now you pick a point, right? And you study this condition, right? Plus this condition, right? So the tensor, the torsion, is a 2 tensor, and it provides another tensor. It's a 2-1 tensor. But instead of a 2-1 tensor, you can think of a 3 tensor with a symplectic form. Right? It's non-degenerate, so you can up and down indices, but with the symplectic form, not with the metric. Okay, so I will think of the element in this way. So what can prove that the condition of being parallel is equivalent to being skew-symmetric in the first two indices instead of the second indices, right? So now what you have to do, you have to split this manifold into irreducible sub-representations of the symplectic group, right? That's down in the literature. Okay, actually it was surprising because it's down but recently, that you can decompose the space of tensors into reducible classes by the action of a symplectic group. But okay, you use, I don't know, basic representation theory results, and it turns out that this space splits into 4 classes. So we have splitting of this vector space of tensors at that point into 4 classes invariant by the action of the symplectic group. So the point is that once you have a tensor satisfying the Ambrose-Singer conditions, and if in one point it belongs to one of these classes, it belongs to that class in the rest of the points of the manifold. So you use that condition again and you try to get information. So we're exploring the information you can get from these classes. And by the way, just to give a glimpse of how these classes are, I'm going to put the structure of some of the tensors belonging to some of them, just to put some instances of the structure of these tensors. So the tensors of the classes are of this type. For example, the class. Thank you so much. Yeah, I think this one goes better. Thank you so much. And the blue goes better. Thank you so much. Okay, so for example, I have some characterization of these classes. For example, T1 plus T2 are tensors satisfying cyclic conditions, right? This sum is a sum of the cyclic permutations of the indices, right? So this is the structure of, for example, this class, or for example, this class is this, or this one, the vanishing of some traces, symplectic traces, V1, 2, and with 1, 3. So that this T, small t, means that the trace of this tensor with respect to the symplectic form. It's like a standard trace, but taking a symplectic basis, right? So with respect to the first and second component, or first and third component, I mean, the tensors are of this nature. And then you want to get information on that. For example, a remarkable result is the following. Okay. For example, if we have a manifold here, sorry, I said symplectic, and I was wrong, it's not symplectic, it's pre-symplectic. Because when you have that tensor, in the spirit of having a geometry defined by a tensor, at the beginning, you don't put the condition of being closed. You have just a tensor, so it's a pre-symplectic manifold. So what actually I had before was a characterization of homogeneity for pre-symplectic manifolds. But we have results like these. Oops. that M with omega, which is a free symplectic manifold, and one of these connections satisfying the Ambrose-Singer condition, then this is homogeneous plus the topological conditions, homogeneous and symplectic if and only if the torsion tensor belongs to this class. So we have a powerful characterization of homogeneity of symplectic manifolds in terms of one of these classes. And the others provide more geometric information, which is under study now, right? So, for free. Yeah, you get symplecticity for free if the manifold has one of these tensors. So the first and second class belongs to the symplectic realm, not only the pre-symplectic case. For example, we have some of these results. Okay, we go further. There is another generalization of Ambrose-Singer theorem in the following sense. Imagine you have a manifold M with a tensor, right? And now, instead of putting here a metric, which was like an old result in the Ambrose-Singer philosophy, imagine you have here just a connection, right? That's a possible situation. Actually, in the symplectic case, that's the Fedosov situation, where a Fedosov manifold is a symplectic manifold plus a connection, right? A symplectic connection, right? So imagine you want to have that. So, and you want to apply Ambrose-Singer theorem. That means you want to characterize homogeneity, reductive homogeneity, by the action of a group preserving the tensors, that is the geometry, but also preserving the connection. The connection means that the action of the group is going to be by affine transformations of the tensors. You cannot apply the result before because this is not a tensor, right? This is not a tensor. This is just a connection. So you have to rebuild the theorem in this case. So in this case, the result is reductive homogeneity if you put the topological conditions. If you take these topological conditions out, you have the characterization always of locally reductive homogeneity, where you have to give a precise definition of what local reductive homogeneity is, because it's not simply the splitting of a Lie algebra, because you don't have a group, you have a pseudo group of transformation, of local transformation. So you have to pay attention a little bit, but I didn't want to enter into these details. In any case, you have reductive geometry homogeneity, so you need the existence of these connections as usual. If you want to put all the topological constraints or the conditions for globally homogeneity, you have to ask for the completeness of this metric. So you put the curvature as a parallel tensor, you put the torsion as a parallel tensor, then you put the tensors as parallel tensors. So far so good. And what you need is now that the difference between the two connections is also parallel, right? Ah, that's a good thing. Yeah, actually, the statement should be with tilde here, but you can prove that it can be either with this formulation or you can drop this tilde. And I prefer to drop now the tilde here. This R is the curvature of the initial connection, this is the torsion of the initial connection, and this is the difference of these two connections. So if we have that, we can assure the homogeneity leaving this geometry invariant at the same time by the action of affine transformations. For example, there's another nice characterization, and we can apply this to the Fedosov case. Okay. So I still have, I think, 10 minutes probably. It was, yeah, okay, beautiful. 15 minutes with questions. I think it was yesterday, but okay. I will try to stick to my slot. So now, for example, we can apply this to this situation. Actually, it should be the other. Right? This is the so-called Fedosov manifold. And Fedosov condition is that the two ingredients should be connected somehow, that the connection is a symplectic connection with no torsion. It's a symmetric. It's a symmetric connection, right? This is a Fedosov manifold. By the way, this is actually the origin of the definition. Once you have a pre-symplectic structure, and then if there is a linear connection satisfying this condition, then the pre-symplectic form becomes symplectic immediately. So in this case, this is a symplectic manifold, it's not pre-symplectic. So if we apply our results here, we are directly classifying symplectic manifolds plus a connection, right? And you want to apply this, then the condition homogeneity, reductive homogeneity is, as I said before, the existence is equivalent to the existence of a complete connection satisfying that curvature is parallel, the torsion is parallel, but since the torsion is zero, you drop this condition. The difference is zero, and this condition. This S is the difference between the Fedosov connection and this other connection. Okay, we have this. And now we want to apply the same philosophy. Once we have one of these conditions, so the manifold is going to have a group of symplectomorphisms that are also affine with respect to this connection. Now we split these into classes. So we pick a point, we consider this vector space, and the condition, this one implies, instead of having this 2-1 tensor, you can work with the 3 tensor defined by the symplectic form and this object, so you have a 3 tensor. So this S at that point belongs to a symmetric tensor. Here you can verify that the condition, this condition means this. So now we have to split this into irreducible classes under the action of the symplectic group. So in that case, you have some easy representation theory working, and you have that this space splits into 3 classes, right? The idea was now trying to get information from these classes. It happens that every time you have one of these decompositions, for example, the initial one of the original Ambrose-Singer theorem, where there were also 3 classes, or for the pre-symplectic there were 4, or even if you put other geometry together with a metric, for example, the Keller case, where there is the metric and the almost complex structure, there are 4 classes, or in the quaternion-Keller case, where there is the metric and the quaternion-Keller structure defined by a 4 form, there are 5 classes. I mean, you can do the same trick many times as the geometry you want, your favorite geometry. Okay, you have these classes, this decomposition. You always look at the decomposition, and there is always at least 1, sometimes 2, classes of this decomposition of small dimension, right? So the space of tensors, this space of tensors, the dimension of them is n times this space of symmetric tensors is n cubed of the order of n cubed, the dimension of these. So that means that this decomposition, the sum of the dimensions of each of them, should reach this number. But it turns out that one of them is small, right? It's just n. It's a small one. That happens also in the initial case, Ambrose-Singer, the 50s, where there are 3 classes and the first one is very small. As you can remember, when I put some of the geometric results of these classes, I said that being in the first class meant that the manifold had constant curvature. That's a strong condition, actually negative constant curvature. Locally, you are the hyperbolic space. And that hard, strong condition for the homogeneous space, now there is an explanation why this class provides such a strong condition. It's because this class is small. I mean, you cannot provide a strong condition with the majority of the tensors. Just a selected selection of tensors, the dimension of which is small, produce a strong condition, right? So now it happens in the symplectic case, or at least in the Fedosov case, that one of the classes also have this property, that the manifold, sorry, the first class, the connection is not a polynomial of degree 3, is not a polynomial of degree 2, but it's a linear polynomial, and this is the reason this T1 is called linear class. So every time you have a linear class with any geometry, go to that class and try to find a strong geometric result that will be behind. There is always a surprising result. So that's what we did. We tried to see how, or the information we get from an Ambrose-Singer connection being here. And the result is as follows. We were expecting something connected with some curvature or something, and it's not really that result. It's more of mechanical nature. So the result is as follows. If we have a Fedosov manifold, and you have one of these Ambrose-Singer connections such that the tensor belongs to T1. This tensor, recall that this is the difference between your Fedosov connection and the connection appearing in the Ambrose-Singer theorem. This is Ambrose-Singer connection, Ambrose-Singer. Okay, then this tensor, as it belongs to a class of dimension n, is labeled by a vector field. The reason this class had such a nice dimension, the same as the dimension of the manifold, is because at each point, one of these tensors is defined by a vector. And if this tensor now you span it along the manifold, there is a vector at each point and you have a vector field. So one of these classes belonging to T1 is defined by a vector field. So the characterization now is that this vector field in a symplectic manifold, you do mechanics immediately, you have a Hamiltonians, the Hamilton equation. So the manifold is foliated by the different leaves of a Hamiltonian of the Hamilton equation, right? Plus or minus, whatever you want for the Hamilton equation, right? So you consider this vector field, so you consider the Hamiltonian form. If the manifold had these nice topological conditions, that is simply connected, you can define a global H, otherwise you have local H. In any case, you consider the leaves of this, and then it turns out that the leaves are totally geodesic, or in better words, the connection, the Fedosov connection restrict to the leaves. The leaves are totally geodesic. And flat. So that's funny. So the analogous of having constant negative curvature in symplectic geometry is having a Hamiltonian foliation of totally geodesic and flat leaves, right? You can put it either in the global setting or in the global or the local. If you put local, then the H is a local function and so on, so the foliation you have to pay attention because it's a local foliation, then you have to glue the different foliations with a covering. It takes a little bit of energy, right? Actually, we explore a little bit this situation. We have instances of manifolds satisfying this. And then, by the way, Jose Luis, and then I look for that in the literature, and these special kind of mechanical systems in physics, they have special attention. They put some attention, so I don't know why they're not so far very important in mechanics for different reasons of integrability, and it turns out this integrability now is connected with this algebraic Ambrose-Singer connection, so that's something to explore in the future, right? And I just want to say just one word more, because when we were studying this, we were worried about the possibility of building something which was completely connected with the non-results. Let me explain myself. So once you have all these homogeneous space, for example, in the symplectic case, can we put a metric, a Riemannian metric, so that these tensors can be also regarded from the Riemannian point of view of Ambrose and Singer, which is, the question is interesting by itself, but at the same time, I was a bit worried of trying to build a classification of tensors, which could be somehow obtained from the original classification of tensors by Ambrose and Singer and Tricheri and Van Ecken. And the answer is not. Actually, and that's going to be the last result, is to give peace to myself. So actually it's not so important. But it turns out that there are examples of pre-symplectic manifolds, or Fedosov. Actually, you can put it with Fedosov, which is fine. So you are in the symplectic case. where, and of course, plus one of these Ambrose-Singer connections, so you have homogeneity or local homogeneity, where you can prove that there are, or there is no metric G such that this. So that means that there are instances where this construction doesn't fit or will never fit in the standard Ambrose-Singer theorem, and the information of the tensors will be new somehow. Sometimes yes, you can have that, for example in the Keller situation, where the symplectic manifold has also a metric, but sometimes not. So this is a completely separated theory. Right? So plan for the future. That's something that we would like to do, is to get more information of the classes and extend our result to other geometric structures, not necessarily symplectic, and not necessarily metric. Right? So thank you very much. I think I'm over with this and perfectly with the time. And I'm open to your questions, but unfortunately we cannot scroll through the transparencies if you want to make questions. I'm going to be always with a whiteboard again. Thank you very much.